Hey, good morning. We have 6 folks. I'm going to give a few minutes for a couple other folks to join in, and then we are going to begin just solving some problems. I think at this point you guys have seen pretty much all of the theoretical or technical stuff, detailed stuff that you need to complete this section on logarithms, but that doesn't mean we don't need lots and lots and lots of practice. So we're going to begin getting that lots and lots and lots of practice today. In order to try and make this as useful as possible, I will be grabbing stuff from your homework. So if there are particular problems that you are hung up on, it would be a good idea to type those problems into the chat. So let me know which problems you guys want to see worked as examples, and that way I can make the best use of all of our time. I'm going to be speaking a little bit quietly today. Something of a sore throat. I can feel my voice starting to go. So if you have trouble hearing something, same thing. Just go ahead and interrupt me either in the chat or by holding down spacebar to talk, and let me know what it is you need me to repeat. Oh, come on. No. Okay. Yeah, look at us. We're almost there. So I think we should focus on stuff from homework 20 and 21 today. Still just 8 here. All right. I'm going to pull up homework 20. I was just saying, if you're just now coming in, today's pretty much going to be just working examples. We're going to spend time practicing those properties of the logarithm that we discovered last time. So maybe on the board behind me, I will go ahead and remind you what those basic properties are. All the animals are here today. Let's give these a try. So these are the three kind of crucial algebraic properties of the logarithm. I'm not including the definition here because that's a definition, not an algebraic property. And I'm trusting that you guys remember the definition of the logarithm since we've been working with these for a minute now. The first few problems in your homework ask you to compare particular values. So they give you, log of this minus log of that, and they ask you to compare it to one other thing. So I could ask maybe, it's okay, Hamlet, it's okay. This one. Example, we might want to ln 56 minus ln 7. Yeah. Ln of 8. So you can grab your calculator, and I encourage you to do so along with me here. Type in ln of 56, close parentheses, minus ln of 7, close parentheses. And you see that the ln of 56 minus the ln of 7 is 2.07944. So this, and then if I calculate this guy, I ask just for the ln of 8, I get the same thing. And so the purpose of these sort of exercises, which are the first few exercises in homework 20, is to get you to feel more comfortable with what's going on here in each of these properties. If I had to explain what's going on here, I would say these are the same because these are equal because ln of 56 minus ln of 7, according to property 3 here, is the same as ln of 56 over 7. All right, subtracting on the outside is the same as dividing on the inside. And then 56 over 7, well, that is 8, right? 8 times 7 is 56. It's important that we use these properties precisely as they're written down there. Meaning, here I have subtraction outside and division inside. I don't ever have division outside, all right? So this is not the same as ln 56 over ln 7. They're very different. So ln of x minus ln of y is the ln of x over y, which is not the same as the ln of x over the ln of y. And that's what I mean when I say you have to use these properties exactly as they're given. Any questions on what's going on here? So let's fiddle with one or two more of these. And then we're going to kind of ramp it up a little bit. So which one of these properties looks like it could be applied to this? Well, here I have something times a log base 10, remember, a here is 10 if you don't see anything written, just like ln means base e, log with nothing written means base 10. So I've got 8 times the log base 10 of 2. That kind of looks like this to me, 8 times log base 10 of 2. So I'm expecting that these will come out the same, because 2 to the 8 is 256. Maybe this time I'll do the comparison calculation via that screen share tool, so you can see how I'm putting this in the calculator. Where is it? Okay. So I'm going to share with you my virtual TI-83. I want to compute the log, oops, sorry. I actually want to compute 8 times the log of 2. I'm being very careful with my parentheses like this. Hit enter. I see it's about 2.408. And separate from that, I calculate the log of 256. I see that that's also 2.408. So what's going on here is I can apply property 1 to bring that 8 inside. Was Zoom freezing? Tell me Zoom isn't freezing. No, we're good. Okay. I can use that first property over there to bring the 8 inside as a power, and I'll show you what I mean. So these are equal, or at least from my calculator, these appear to be equal. This guy, and that guy, we're both about 2.408. So the reason these are equal is property 1. I have right over here. 8 times the log of 2 is by property 1 the same as the log of 2 raised to the 8th. And again, I'm being very careful with my parentheses, right? It's 2 to the 8 that's inside the logarithm. If this 8 was outside the parentheses, that would mean something different. But then 2 to the 8 is 2 times 2 times 2 times 2, blah, 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 8 times. That is 256. So any questions on these comparison type problems? Where we use the properties of logs, or we verify the property of logs for the specific numbers? Okay. Then let's start to ramp this up a little bit. Each of these properties can be read from left to right or from right to left. Yeah, like I could take something like this and rewrite it like that. Or I could take something like that and rewrite it like this. If you move in the direction that makes the statement take up more space on the page, we call that expanding. And if you move in the direction that makes it take up less space on the page, like taking these two and rewriting them as the single logarithm, we call that contracting. So the 8th problem in homework 20 says to expand the natural log of x times y to the 9, all divided by z squared. all divided by z to the 7. I'll write this a little bigger. The order of operation stuff matters here, and you need to be good with your exponent rules, just like you needed to be in the previous class. It's important, for example, that you recognize that only the y is being raised to the 9th power, and only the z is being raised to the 7th power. So those powers are attached only to the associated variables. And if it was going to be any other way, we would have to indicate so with some more use of parentheses. I want to expand this, which means I want to go in this direction. So from stuff like this towards stuff like this, or from stuff like this towards stuff like this. And the way I think about it is to look at the inside of the logarithm and ask, what is the outermost operation going on? When I look at the inside of that logarithm, the outermost operation I see going on is the division. And that division bar is like a grouping symbol. So first I'm going to do something involving property 3. Because I have division inside a logarithm, I know I can write that as subtraction on the outside of the logarithm. The base A for this problem is E. And we write that as the ln. So getting used to this notation is another important part of developing the necessary logarithm skills. So since I do have division inside a logarithm, I can rewrite that as subtraction outside the logarithm, meaning I can write this as the ln of the numerator minus the ln of the denominator. And again, I'm being very careful with my parentheses to show that those powers are just attached to the appropriate variable and that the powers are inside the logarithm, not outside the logarithm, because that would mean something very different. So this is a good first step, but it's not the whole thing. Each of those two pieces that I get out of this step, the ln of x times y to the 9 and the ln of z to the 7, can be further expanded on their own. That first guy looks like something I could use property 2 on, because I have multiplication inside the logarithm. The second guy looks like something I could use property 1 on, because I have a power inside the logarithm. Here, I can bring this 7 down in front of this ln. Here, I cannot bring this 9 down in front of the ln before I split it up, because the x is not being raised to the 9, only the y is. And that's another instance of me saying you need to use these formulas exactly as they're stated. So before I can bring the 9 down, I need to split up the first log. I can go ahead and bring the 7 down in this step. Because this is the first one like this that we've done, I'll do them in separate steps. So first, splitting up this log. That is the ln of x plus the ln of y to the 9. I'm going to leave this ln of z to the 7, not doing anything to him right now. Now there's no more multiplication or division going on inside my logarithms, but those last two, they do have some powers going on. And so I can apply property 1 to those, bringing the powers down in front of the respective logarithms. The ln of x stays the ln of x. This guy, though, becomes 9 times the ln of y, following rule 1. This minus is this minus, and this 7 can now come down also, same thing. And that's my fully expanded version. Observe that any factors or pieces of the inside of the original logarithm that were upstairs, the x and the y, are positive here. And any piece that in the original logarithm was downstairs is negative in the expanded form. That will always be true. As you work these problems, you're going to be tempted to skip steps. You're going to be tempted to try and jump down to an answer like this without going through those two in-between steps. I caution you against that strongly, because it's easy to make little mistakes and then never be able to find where you made the mistake. But by breaking it down into steps and applying just one of these properties at a time, you can expand or contract pretty much anything, no matter how big or scary the statement is. Questions on this example? Everything feels pretty reasonable, pretty comfortable? Too much. Okay. So we'll keep ramping it up just little bits at a time. Here I want to combine some logs, so I'm looking at the 12th problem in homework 20 now. And I have a comment here. The homework actually writes these without the parentheses. Writes them like this, which is terrible notation. Please don't do that. Okay, this is one of the ways Pearson sucks. I haven't been able to convince Pearson to stop sucking. Always put the inside of your logarithms in parentheses to make clear what's inside and what's outside. If this square, for example, was out here, that would be very, very different than having the square in here. The square in here says take k, square it, multiply by 5, then take the base 9 log of that. The square out here would say take k, multiply by 5, then take the log, then square. So it's an order of operations thing. And it's a shame that Pearson gets so lazy with their notation. I certainly wouldn't mark something wrong if you left that off and did everything else correctly. But I think if you get into the habit of writing these parentheses, you'll make fewer mistakes and you'll understand what's going on better. I could expand this if I wanted to, using property 2 and then property 1, right, to split this multiplication, the 5 times k squared up, and then using property 1 to bring the 2 down. But that's not what they asked me to do. They asked me to combine these. So instead, I'm going to use property 2, because what I have here is 2 logs of the same base, both base 9, being added on the outside. That means that's the same as the single base 9 log of the insides multiplied. Like this. And then 2 times 5k squared is 10k squared. So Here we're going in the other direction. Instead of trying to pull them apart, we're trying to put them together. Questions on this example? Please, if you have questions, ask them. It's very much worth your time. Questions on any of these examples so far? Okay. We'll do one more like this, and then we're going to change gears just a little bit. So here I'm given 3 ln x minus 2 ln y plus 5 ln z squared. Each of those has a property one thing going on. Each of those has a number out front that I can bring in as a power. And that would be a good first step. Okay, remember, try to just apply one property at a time. So I don't want to use either of the other two rules in this step. I'm just going to use one rule at a time. So by property 1, 3 ln x is the same as ln of x cubed. This guy can come inside. 2 ln y is the same as, and the minus is going to stay out front, because I'm just bringing in the 2, same as ln y squared. And the same thing here with this 5, but here I need to be a little bit careful. This will be the ln of z squared raised to the 5th. So if I take z squared and I raise that to the 5th power, that's the same as z raised to the 10th power. So I know it might feel silly, but I'm going to give that its own line. I don't want to be doing too much in any one step. Just trying to keep my work nice and clear and organized. That is the key to solving hard algebra problems. Now I have a choice. I could combine these two using property 3. I could combine these two using property 3. I could combine these two using property 2. No matter what I choose, one of them is going to be left out in this next step. And so I'm going to have to do at least one more step after that. To me, the most natural thing to do, this looks like this to me. The base a here again is e because we're writing ln. It's the natural log. So I would take these two guys and write them as the single ln of x cubed over y squared. And then this fellow is just coming along for the ride. The subtraction outside is the same as this division inside. Note this is not the same as, and this is a mistake I see all the time, so please hear me when I say this. This is not the same as ln of x cubed divided by ln of y squared plus ln c to the 10. This is not the same as this. Totally different animals. Probably the single most common mistake I see in any of these problems is writing something like this, where you've got a log divided by another log, instead of writing something like this, where you have a log with the division inside. A single log with division inside is not the same as two logs being divided on the outside. If you wrote this, it would be wrong. Now, in my last step, I have ln of something plus ln of something else. That's something I can combine using property 2. So I can write this now as the single natural log of x cubed over y squared times z to the 10. And while we're at it, practicing our fractions, if I want to multiply these, this z to the 10, he just goes upstairs, because he's z to the 10 over 1, and you multiply the fraction straight across, and it looks much nicer like that. So I'll say this is ln of x cubed z to the 10 over y squared, like that. Questions on this? Please make sure that you're getting this in your notes really nice and careful. Having examples like these to look over will be really important as you do your homework. We all see where each and every one of these steps is coming from. If you are comfy with these, then the next thing I would like to do is look at solving a few equations. So this is homework 21 stuff. There's a couple at the very end of homework 20, and so maybe I'll start with one of those. There's two types of equations that we're going to learn how to solve that previously we really hadn't been able to. The first type is one we've seen a little bit of already this week, exponential equations. Equations where the variable is in an exponent. Taking a logarithm will allow us to get it down. The other is a logarithmic equation, where the variables are stuck inside of a log, and we'll need some new trick to get those out. Let's do an exponential equation first. So maybe I have an equation like this. Some number like 1.6 being raised to the power of x. And I want to find out for what power x is that equal to 5. This is definitely not the sort of exponential equation that I can solve using the one-to-one property, because I have no idea how to write 5 as a power of 1.6 off the top of my head. That's the whole thing. And there's no simple algebra steps I can do to make a 1.6 appear on the right or to make a 5 appear on the left. I could use the definition of the base 1.6 logarithm to say that x here is the base 1.6 logarithm of 5, but 1.6 is such a weird number to use as a base for a logarithm. I would like to solve this either in terms of the natural log or in terms of the common log, or some other log that's a little less weird feeling. And what you're going to find is that most people use the natural log for pretty much everything. So if I wanted to solve this equation, my very first step is going to be to take logs. And I'm going to take the natural log. I guess really I'm going to take ln of both sides, because that's the natural log, which is the most often used logarithm. If I do that, then this becomes ln of 1.6 to the x equals ln of 5. And now the magic of logarithms is that by that very first property, I have a log of a number raised to a power. This power can come down. So this becomes x times the ln of 1.6 equals the ln of 5. What that did is it transformed this exponential equation, where the variable is in the exponent, to a linear equation. X times some number equals some other number. Now, these numbers are weird friggin' numbers, but they are still just constants. So I can solve for x by dividing over by this piece. I can't divide over by 1.6 and cancel the 1.6. Nothing like that works, because the 1.6 is inside the logarithm. This ln of 1.6, though, is just a number. So if I had x times 2 equals some number, I would divide both sides by 2. Since I have x times the ln of 1.6 equals some number, I'm going to divide both sides by the ln of 1.6. So this is x equals ln of 5 over the ln of 1.6. Now here's a question. Can I cancel the ln's? Is ln 5 over ln 1.6 the same as 5 over 1.6? That looks like it could be done, right? Just in the shape of the algebra. Let's check in our calculator. So I'm going to share my virtual TI-83 again. On the one hand, I know that my answer is ln 5 divided by ln 1.6. So let's turn this on, clear it out. ln 5, close parentheses, divided by ln of 1.6. So I get about 3.42. If I could cancel those ln's, then this would be the same as 5 divided by 1.6. Let's see what 5 divided by 1.6 is. 3.125. Not the same number, right? Not even close. So you cannot cancel those ln's. In other words, this is function notation, right? This is not multiplication. When you see the ln of 5 like that, that's not ln times 5. ln on its own doesn't mean shit. But it is the natural log of 5, which is the output of the natural log function when you feed it the input 5. And those are different animals. So when we computed this in our calculator, the correct one, the first one, ln 5 divided by ln 1.6, is 3.4243. This is approximately 3.4243. This would be the exact answer in terms of logarithms. That would be the decimal approximation to the answer. And you need to pay attention to which any given question is asking for. Oftentimes we want both. General exponential equations can all be boiled down to something like this. Sometimes you'll need to do some sneaky algebra to factor or rearrange the equation to get it into something like 1.6 to the x equals 5. But always you're going to arrive eventually at some statement like that, and then you will take logs on both sides, usually a natural log or a common log, because that's the the ones we have buttons for on our calculator, and those are the logs that just people tend to like to use. And then you'll solve the resulting linear equation for x, or whatever your variable is, and get these two different forms of an answer. You'll have the exact form, which will have logs in it, and then you can put that into your calculator carefully to get a decimal representation of that answer. But the decimal representation is not exact. It's an approximation. It's been rounded. That number, ln5 over ln1.6, is an irrational number. So its decimal representation goes on and on forever and never repeats, kind of like pi. So just like 3.1415 is an approximation for pi, 3.4243 is an approximation for ln5 over ln1.6. Questions on solving exponential equations like this using logs? Okay, so the last kind of clean, simple example I have for you here is an all-new type of equation. The 17th problem in your current homework looks like this. This is different than an exponential equation because my variable isn't trapped in the exponent anymore. Now my variable is trapped inside the logarithm. And just like we said in the previous problem, you can't like divide by ln here to get this x alone. You're going to have to do something else. First, I want to isolate the logarithm. That means I'm going to divide both sides by 6. This is fine. But then I need to undo the log. Like I said, we cannot divide both sides by ln now. In other words, this is not the same as saying x equals negative 10 over 6 divided by ln. This shit doesn't make sense. This has no meaning. I do see stuff like this from time to time. Please, please don't do it. All right, that's no good. Because this ln here, this isn't a number. It's a function. So if this was the square root of x equals negative 10 over 6, you would square both sides. Since this is the ln of x equals negative 10 over 6, I need to do whatever has the same relationship as squaring to square roots to ln. And the magic new word here is exponentiate. Which means to put in the exponent of. I'm going to exponentiate on both sides. So just like taking log of both sides is an allowable operation for equations, exponentiating on both sides is an allowable operation for equations. Since the ln is the base e logarithm, I'm going to exponentiate base e. And I've heard a lot of calculus students just refer to this as eing both sides. I'm okay with that. If you like saying it that way, that's just fine, if that helps you remember what you're doing. So we're going to put both of these in the exponent of e. So ln x becomes e raised to the ln x. I put ln x in the exponent of e. And negative 10 over 6 becomes e to the negative 10 over 6. I put this side in the exponent of e. Why is this nice? Because e raised to the ln of some stuff is always just that stuff. The left-hand side simplifies to x. And that's your solution. X is equal to e raised to the power of negative 10/6. I could again use my calculator to get a decimal approximation. So I'll do that for you now. And then we're going to check that solution in our calculator. So here, let me share my screen with you so you can watch as we do this. First, I'm going to get my decimal approximation. So I will calculate e raised to the power of negative 10 over 6. And I'm being careful with my parentheses, right? If I just type that as e to the negative 10 without any parentheses and then divide by 6, it's going to give me something different. It's going to take e to the negative 10 and then divide that result by 6. Here what I want is e raised to the power of negative 10 over 6, which is its own thing. So as a decimal, this is 0.1888. And we can check that this is actually a reasonable solution to the original equation, or at least a good approximation to the solution to the original equation by plugging it in. So if I take 6 times the natural log of 0.1888, I should get something very, very close to negative 10. And I do. Negative 10.0024, blah, blah, blah. If I use more precision in my approximation, so if I check 6 times the ln of 0.1888756, then I get something much, much closer to 10. So you use a better approximation, you get a better result. This is everything that you need to finish homework 20 and really pretty much all of homework 21 also. I mentioned that every exponential equation will boil down to something like the last example we did. Every logarithm equation will boil down to something like this. But that boiling down process, that can be a little bit tricky. So on Friday, we're going to spend most of the class time, just like we did today, solving problems. And they're going to be solving exponential and logarithmic equations. And I'm going to show you some of that sneaky, tricky algebra stuff that you might need to do in order to boil those complicated equations down to simpler ones like these. It's important, though, that you get comfy with these fundamentals. So feel free to rewind, rewatch this video once it's up on YouTube. Look at these examples while you're working through the homework. Many of them are the same or super similar to the examples that are in your homework, or the problems that are in your homework. The other thing I want to do on Friday is talk with you guys about exam 3. So we are getting close to exam 3. I think it will probably be not the beginning of next week, but the middle or the end of next week probably. So on Friday, when we meet, I will let you know how that's going to go. It's going to be in my math lab, and we're going to use honor lock to proctor. And that will also be the system that we use for the final exam. So that's where we're at. Hopefully you are all done with homeworks up through 18. If you're still working on 19, that's okay. Try to get it done. And you need to get into homeworks 20 and 21 this week. You need to be done with 20 by Friday, hopefully. And then if 21 takes a little bit longer, that's okay. I'll look into extending it. I'll pay attention to where you guys are. I want to work with you. But please work with me also, okay? Don't lose steam now. This is the hard part of the class. As long as you keep that energy up just a little bit longer, then the rest of the semester is going to sail by and you'll do just fine. So please grind on those homeworks, 20 and 21. And I will see you guys on Friday. Any last minute questions? Okay. Have a good morning.